Hi, this is Phil Koopman, and I'll be talking about Safety Performance Indicators, SPIs, for self-driving cars. Let's start with an overview. KPIs, key performance indicators, those are the things you've probably heard about before, quantify performance. They're important, but not enough to get to safety. In addition to KPIs, you need SPIs, Safety Performance Indicators. Now, these are also quantified indicators, but they're about safety, not about performance. And there's an important difference we'll discuss. There are leading and lagging SPIs, and there are safety case validity SPIs. So let's get into it. Key performance indicators, KPIs, are quantifiable measurements that are typically used to gauge statistical performance. So on the dartboard picture, the KPI might be the distance between a dart and the center, and good KPIs indicate that the darts are more or less clustered around the center, and bad KPIs for this case would be some dart or many darts being further away. So a KPI might be something like the average distance the dart is to the bullseye. In terms of self-driving cars, what you'd expect are KPIs are things like the percent of correctly identified pedestrians, and the miles between self-driving car disengagements, and the miles between uncomfortable braking. Now, those things have a little bit to do with safety, but if you never uncomfortably brake, and if you go 1,000 miles or 10,000 miles without a disengagement, that means your car is probably working pretty well, but it's nowhere near enough to be safe, as we'll get to. KPIs can measure self-driving car progress if they're chosen carefully and applied in a reasonable way, and you'd expect the metrics should improve over time. And while you're still trying to get the car to work, KPIs are probably a good area to concentrate on, because after all, if the car can't go 500 feet without having some sort of misbehavior, then that's not about safety. It's about it doesn't really even work yet. But KPIs, as good as they sound, are the wrong approach for safety, and we'll see why momentarily. What it boils down to is KPIs are really intended to help with quality. Are all the functions working? Is the functionality improving? Is the fault rate generally decreasing? In other words, are you getting closer to a self-driving car that seems to be working pretty well? That's great for knowing whether your self-driving car is more or less working. It's not enough for safety. Let's see why. Good KPIs are important, but they're only the start. Here's a picture of a Gaussian distribution, a normal distribution showing 3 sigma, so 3 standard deviations. And you can see if you look really carefully, there's a little bit of the curve visible past the red bars, but pretty much everything is inside there. So as long as the 3 sigma is pretty narrow, your quality is probably okay. 6 sigma quality goes further and says, well, we want to basically have almost 0 defects, and we're going to say almost 0 is 5 nines, so 4 defects, 3 or 4 defects out of a million. And that's 6 sigma, and you can see how big that range is. Visually, you can't see anything under the curve between 3 and 6 sigma, but it's there, just a few things. So what that means is that all the way down at the tails of the curve, you're only going to have 3 or 4 escapes out of a million things that you make that turn out to be defective. 3 or 4 in a million sounds great, and for quality, that is really good, and that's what people strive for. But for safety, it's not near good enough. You need a different approach than quality to get safety. Fatal crash avoidance, for example, is 11 nines, not 5 nines, 11 nines. And that means safety is 1,000,000 times more demanding than quality. It's out at about 8.3 or so sigma. Now, 1,000,000 times sounds like a lot. Well, this is an example, so the real number will be somewhat varied from that. But what I said is, well, you've got a mile of driving, and every 5 feet there's a chance to make a mistake, not recognize an object, make a wrong turn, something like that. And I just used 5 feet sort of arbitrarily. And I said, well, 250 miles between fatal crash, because human drivers are around 100 million miles, but that includes all the impaired drivers. We want to do better than that. So let's say that 250 million miles is a good target. It might be higher, it might be lower, depending on the company. And we applied a traditional 1.5 sigma shift. If you go look up 6 sigma, that's a typical number. And what you get is 11 nines. Well, if you need to be 1,000,000 more times than 6 sigma, and 6 sigma is considered kind of almost 0 defects, that's just on a whole nother scale. So normal quality approaches aren't going to get you to safety. Let's dig down a level and talk a little bit more about that. Let's start again with KPIs. KPIs are about functionality. Are all the features implemented? Does each feature work as intended? Are all the scenarios accounted for? And in general, does the product do what it's supposed to do? So KPIs are about, is our product doing what it's supposed to do? Safety goes beyond KPIs. It's not about, does it do what it's supposed to do? Well, of course it does what it's supposed to do. That's quality. Safety is more making sure nothing bad happens, that it avoids doing things it's not supposed to do. For example, are there any dangerous misbehaviors? Do you have any dangerous gaps in the operational design domain? And these are gaps that you might never have seen in testing, but they'll happen in the real world. Are there dangerous gaps in fault responses? Are there dangerous defects in requirements, design, repair, etc.? And generally, if these things happen all the time, you would have seen them in testing, and you would have caught those with KPIs. Safety is really about that other 6 nines worth of quality beyond KPIs, the really rare things that are going to happen all the time in the fleet, but you'll probably not see them in testing. So in order to get a good SPI, you need an indicator. It's a quantifiable measurement, but it's not about traditional quality. It's about safety. And typically, safety is about the arrival rate of adverse events compared to some risk budget. And that's inherent just in the simple metric of, for example, fatal crashes per 100 million miles. That's an arrival rate of something that's bad, and 100 million, 250 million miles between events. That's a lot of zeros. These are rare events, but you still need a way to measure and predict how safe you're going to be. It's common to divide metrics into 2 types, leading and lagging. Lagging metrics are metrics that don't happen until after you've actually deployed the product. An example metric might be loss events or crashes per hour, and that's going to be an extremely small number. For example, 1 over a million crashes per hour. Incidents are also lagging SPI metrics. Now, an incident is something that could have been a loss event, someone could have died, or a car could have crashed, but you got lucky and nothing bad happened. You still want to measure these because that's dangerous behavior and eventually you will get unlucky. For example, running a red light or driving the wrong direction in a one-way lane, maybe you get a crash, maybe you don't, but that's certainly not something you want to see. So if lagging metrics happen after deployment, leading metrics are things that happen before deployment. So system-level leading metrics might be road test incidents caught by a safety driver. So nothing bad happened because a safety driver prevented it, but in fact, it could have been bad if there hadn't been a safety driver. Or if the car crashes during a pure software simulation, well, the good news is it was only software, so no real harm was done, but that's not something you want to have happen in the real world. So these are leading SPIs because they predict the on-road performance to some degree, but it happens before you deploy. Now, while system-level leading SPIs are basically analogs of the lagging SPIs, you can do better. You can, for example, look at subsystem leading SPIs. For vehicle controls, maybe you look at compromised vehicle stability. You never want your vehicle to lose stability, and if it happens, even though there was no crash, even though at the system level maybe the driver barely even noticed, if you lose stability, that's going to be a problem for you, and you want to know about it and fix it before something worse happens. For path planning, insufficient clearance to an object might be a SPI. So for example, you might say, we never want to be within 1 meter of a pedestrian in a certain situation, and you're 99 centimeters away. Well, 99 centimeters, 1 meter, it's not a big difference, is it? But the point of a SPI was, your path planner should never, ever, ever try and be within 1 meter. And if it consistently tries to be 99 centimeters away, that's a safety problem because you violated your hard limit. So a KPI would say, it's only 1 centimeter, no big deal. But an SPI is going to say, wait a minute, you violated a no-go zone. That's a problem. We have to look into it. Perception, false negatives. Sure, you might get an occasional false negative and say, well, we're at 99.99% or something like that. But SPIs say, wait a minute, false negative, you didn't see a construction worker. That's going to be a problem even if construction workers are very rare. SPIs for prediction might be unexpected object behavior. You expected a pedestrian to stay on a curb and they stepped out into the street. Well, it might be that you stopped in time and didn't hit them, but that does not make it okay that you're having trouble predicting pedestrian behavior beyond what you expected. So subsystem leading SPIs are the subsystem has a requirement to have some sort of performance, and you're violating that performance requirement in a way that is dangerous as opposed to just a little bit of jitter. There are also lifecycle SPIs. For example, maintenance errors or invalid configuration installations. Those are the things you want to keep track of, and when they happen, that predicts that you have an issue with your safety, even though it does not directly lead to a crash event. Now let's set SPIs aside for a second and talk about safety cases, and then we're going to see how SPIs plug into them. A safety case claims that a system is safe because there's some explanation of why, for example, some arguments, here's why we think we're safe, maybe some subclaims, some subarguments, and there's some evidence supporting that explanation. Hidden in the safety case are typically some assumptions. We'll talk more about those, but are things that have to be true for the safety case to actually be valid. For an example, an argument might be this, that a self-driving car misses pedestrians because the pedestrians are detected with 3 sensor types. And even if one misses, it's okay. The pedestrian intent is predicted accurately because you have data saying that your system works really well. That's the evidence. And path planning leaves a buffer zone around pedestrians, so even if you're a little bit off, there'll be a buffer zone, it'll still be okay. That might be the type of thing you see in a safety case. Well, what do SPIs do for a safety case? What they do is they help detect violations of the safety case. So some of the SPIs are performance type metrics, except about whether you cross a safety threshold, but some of them actually get straight to the validity of the safety case. Now, the way SPIs can help with a safety case is they measure safety case assumptions and tell you whether the safety case is really true or not. For example, anytime the ODD does not match the operational domain, you want to know about it. Even if you did a safety stop or something like that, you still want to know it happened, and you want to make sure it's not happening more often than you expected it to. You may think that validation predicts operational performance. Well, you want to monitor the operational performance and, for example, notice that there's some mismatch that indicates a simulation validity error, because you may have decided that you're safe because your simulation reflects reality, and you want to measure whether that's really true or not. There might be a SPI about maintenance being performed as required and as often required, because you may have an assumption that maintenance will take care of some things that you don't have to check at runtime. And you may want a SPI to make sure the configuration installed in a vehicle is correct, and anytime you detect that sort of problem, that's something you want to measure and report out. So all these measurements have to do with assumptions in the safety case. The safety case assumes, for example, the software installed in the car is the software that's supposed to be installed. And every time that's incorrect, that means the safety case is invalid, and that's the kind of number you want to track. So, for example, some safety case related SPIs might be that you assume some objects are rare and events are rare, and your safety case doesn't have to deal with them because you decide they'll never happen in your ODD. Well, when they happen, you want to notice it, and you want to say, wait a minute, that thing that was never supposed to happen just happened 3 times yesterday. We have a problem with our safety case. We're going to have to change our safety case to account for them. Maybe you have correlated diverse sensor detection faults. There are 3 sensors, and you said, well, 2 of them will never fail the same way on the same thing. And if there's a way to know that, in fact, they did fail to detect the same thing, that sort of blows your independence assumption, and you can no longer say, well, we have 3 sensors and 2 will never fail together, because it just happened, and we have some data to show it. And you probably want to track your safety-related maintenance errors, because if you're assuming that there are no maintenance errors and they happen, that invalidates your safety case. Let's do some concrete examples that compare and contrast KPIs with SPIs. For example, you might have a distance to an object. A KPI is probably going to measure average and perhaps 95th percentile clearance. So if you say, all right, we want to be 1.5 meters away from pedestrians in a particular situation, and our average, sure enough, is 1.5, and our 95th percentile is 1.4, that's great. Well, that says you're doing what you want to do, but it doesn't really speak to safety, not directly, because the SPI is more like if you have a 1 meter hard limit keep away, you say, how often does the self-driving car violate the safe clearance limit? 1.01 meters? No problem. 0.999 meters? Well, no, that's less than 1 meter. That's a safety problem by definition, even if your KPIs say most of the time you're doing great. Another example is sensor effectiveness. The KPI might be the detection rate and the signal-to-noise ratio, things like this. Well, those all tell you if your sensors are working well. But for the safety case, you may be, as we mentioned before, arguing that you don't have concurrent multi-sensor detections. Or maybe you have 5 sensors and you argue that you'll never get 3 of them missing a particular thing, so you say if 3 see it, we're good to go. Well, if you're assuming random independent failures, you might want to have an SPI to test that. So if you say 3 out of 5, that's great because they all fail independently and no 2 fail together, so the odds are really low they'll all fail. And your data shows that 2 sensors are in fact failing together all the time. The SPI showing the correlated failures is what matters because it undermines the independence and argument in the safety case. To be clear, that SPI is not indicating that you're unsafe. That SPI is indicating the assumptions in the safety case are invalid. So you don't really know if you're safe or not in the long term. What you know is your safety case is based on a false assumption. SPIs might also be lost to calibration. You may say, well, we're not going to drift too far from calibration within one working day. One of the SPIs would be, well, how often do you actually exceed the amount of drift in a working day? And if that happens more than very seldom, then you may need to increase the frequency of calibration. For pedestrian perception, a KPI might be accuracy, precision, recall, the standard things. But a SPI isn't really about that. A SPI might be, I got a false negative for more than a few consecutive frames on something I care about. Even if in aggregate, I'm seeing it almost all the time. If I get a bunch of false negatives in a row, that could be a problem that breaks my trackers, but more likely indicates that I have a weakness in detecting that sort of thing. Or maybe there's a previously unknown type of pedestrian encountered, and you're not used to seeing that, and you would like to know, basically, what the heck was that SPI? If it's happening frequently, then your system might not be mature enough to deploy. In the picture, we see a child next to an adult, and in this particular case, this system would see children alone, but had trouble when children were next to adults. And that's the kind of a thing a SPI should call out, that you're having this one particular situational thing where you're doing poorly, even though on average you're doing great. SPIs can help you with the deployment decision. For self-driving cars, at some point, you're going to have to decide whether or not your system is safe enough, your vehicle is safe to deploy on the roads. And SPIs are going to help you make that decision. If you only have KPIs, they're going to tell you whether your self-driving car more or less works. And even a safety of the intended function SOTF process will find a lot of outliers, but a SOTF process can't find a billion miles of outliers because you probably won't be able to take a billion miles of data. At some point, you'll get to the place where you're saying, you know, we found everything we can find. It's not really practical to do more. As far as we know, the system's perfect, but there's still a probability there'll be some other things. And our KPIs are going to struggle with extremely low frequency events because they're about, is your average close to where it needs to be, and not about the extreme long tails of the curve out where safety lives. SPIs, on the other hand, can help you predict whether it will actually work safely. So SPIs from simulation and testing, but also subsystem levels, will help you realize whether or not you're having trouble responding to things that are kind of rare, but you got lucky, or things that are kind of bizarre, like, for example, in downtown Pittsburgh, the earth opened up and tried to swallow a bus. This is a real thing that happened. Those are the kind of things you say, well, if we have SPIs, we're looking out at the long, long tail of the curve, trying to find the really rare things and make sure we can handle them. Subsystem SPIs go further. So system SPIs are going to be from simulation and testing, system level effects. But you can do even better if you look at subsystem SPIs. So for control and planning and prediction and perception, to try and say, yeah, I know that we haven't hit anything, but in fact, our perception system is having trouble seeing things, so it's just a matter of time before we get unlucky. Those are the kind of SPIs you want to see in a good place before you decide to deploy. Also, the ability of the system to detect and respond to exiting the ODD is a SPI that you'd probably want to take. There are also safety case SPIs. So safety case SPIs generally feel like the arrival rate of surprises or unknown unknowns during testing. Sure, if you get an unknown and you fix it, that's great. But if more unknowns are arriving every day, every single day there's new different unknown unknowns, and some of those are dangerous, and sure, your safety driver does a shutdown and you fix it, but if those keep coming and coming and coming, you're probably not ready to deploy. You want to be in a situation where not only are you safe, and not only did you fix all the problems, but you have a handle on the arrival rate of new things, and it's low enough that it's responsible to deploy out into the world. This largely corresponds to the arrival rate of gaps in the safety case. How many incidents do you have that reveal a defect in the safety case? Well, if you're finding defects in the safety case every day, it's not time to deploy yet. Wrapping up, SPIs predict and monitor system safety. KPIs are about how well do we drive, and SPIs are about how often are we potentially unsafe. How often is our safety case invalid? How often are we seeing things that are not supposed to happen because they're unsafe happen? And those numbers need to be extremely low to actually deploy safely. There are different flavors of SPIs. There's lagging SPIs, such as crash rates, but there's also, more importantly, leading SPIs, such as simulated collisions, testing incidents, and things that have to do with your subsystems not performing the way they should to be safe, even though the system responded properly. And there are safety case SPIs, which are how often is your safety case invalid even though there was no incident, there was no mishap, it's just some assumption in your safety case got violated, and then you have a safety case problem. So here's the question to ask. Do you have good SPI coverage for your system? Sure, you probably have KPIs from your SOTF analysis, but do you actually also have SPIs, and how are they looking? If you want more examples of what SPIs are and how to use them, take a look at ANSI UL 4600 Chapter 16. That's all about metrics and SPIs, and they'll provide some guidance on how to use SPIs to make sure your self-driving car ends up being deployed in a safe way.